So what I'm going to present today is actually work that is unpublished. So it's ongoing research with my supervisor, Yvon Madej, who is in Paris, unfortunately couldn't be here. And then PhD student of Yvon's, Yipeng, was also in Paris. And I would also like to thank in particular Eric Concez and Antoine Lévide for some useful discussions last year in Moscow. Okay, so I'd like to begin with a kind of bird's eye view of the state of the art vis-a-vis coupled cluster theory and the mathematical literature as it exists today. And I'm going to do that by very shamelessly plagiarizing a slide that I see on my former supervisor Benjamin Stamm's presentations. So it's a fun little comparative study. So what we're going to do is we're going to take a few keywords and we're going to input them onto Google Scholar and then math sign it to get a comparison of the mathematical literature versus the scientific literature as well. And I have three keywords here. So there's Navier-Stokes as being representative, a very classical applied math physics field. Density functional theory, which is relevant to people here. And then coupled cluster, which is what I'm going to do. So you take the same keywords that we've inputted into Google Scholar and you put them onto MathSciNet. And for Navier-Stokes, you get about 12,000 hits, which is about 1% of the total literature, which is fair. But what is interesting is when you do the same thing for density functional theory and for coupled cluster, you basically get drops in the ocean. So in particular for coupled cluster, you see that there's only 29 listed articles on MathSciNet. And once you start digging into these numbers, it actually gets worse because only 6 of them, so 5 plus 1, are actually publications in numerical analysis journals. And I'm writing 5 plus 1 because there's a 6th one which hasn't been published yet. It's only available as a preprint on arXiv. So as a mathematician, I'm officially ashamed. Okay, so what are these 6 mathematical unicorns? So it all begins with an article by Reinhold Schneider. So this is Numerische Mathematik 2009. So this really lays the foundation for any kind of numerical analysis for coupled cluster. So basically what Reinhold did is to show that you can derive a priori error estimates for the CC equations in a finite dimensional setting. So you have a finite single particle basis, and in that setting you can derive a priori error estimates, you can derive estimates for the coupled cluster energy. So this was followed a few years later in 2013 by an article by a PhD student of Reinhold. So this is Thorsten Roveda, ISAM M2M 2013, and basically in this article Thorsten shows that you can formulate the CC equations in the infinite dimensional setting. So normally chemists write the CC equations in a finite dimensional space, but Thorsten basically shows that you can also do this in an infinite dimensional setting. You have operators which are well defined on Hilbert spaces of infinite dimensions, everything is bounded, etc., etc. This is followed in the same year by a joint article by Reinhold and Thorsten, where they basically take the analysis from the first article and show that it extends to the infinite dimensional setting. You get very nice error estimates in the a priori sense. Then a few years later, 2018, there's a group of people in Oslo who start working on this problem. So you get an article in SciAm Numerical Analysis about the a priori analysis of the extended coupled cluster equation. So this is a different flavor of coupled cluster. It's based on a bivariational principle, and basically you can show that in this more complicated setting, it is also possible to do an a priori error analysis. And finally, in 2019, so there is a further extension. So you basically do error analysis for yet another flavor of coupled cluster. So this is so-called tailored coupled cluster, which you can think of as a kind of quasi-multi-reference method. So I don't know how many people here were present in the first workshop, but Reinhold talked about this. So this was it was related to the topic of his talk. And we are very fortunate in having the lead author sitting here in the audience. So if you have questions, you should talk to Fabian. The one-line version is that this is basically active space DMRG followed by singles and doubles coupled cluster. And finally, as I said, there is a 6th article which is available as a preprint on arXiv. It's very comprehensive. They do a bunch of things. They show in particular that you can interpret discretization schemes for a coupled cluster in terms of graphs, and they also study the coupled cluster function using topological degree theory. Okay, so the summary is that we have the foundation of an a priori error analysis for CC, but this comes, as I hope to show you in the next 10 minutes, with significant caveats. Okay, and as far as a posteriori error analysis goes, there is nothing. It's a post-apocalyptic wasteland. And this being the case, if we want to develop an a posteriori error analysis, there's at least a couple of basic ingredients that we need. So first of all, we need some kind of a quantitative relationship between the CC error and the CC residual. The CC error is the thing that we would like to know about, and the CC residual is the thing that hopefully we have some way of accessing. So when I say hopefully we have some way of accessing, that's actually point number 2. So it's non-trivial to be able to understand how the CC residual behaves and to be able to bound it. It's a very high-dimensional object, so this is really also something that requires a lot of work. Here in this talk, I'm only going to focus on the first point because this is difficult enough as it is. And it's also related to, by the way, I should mention the a priori analysis. So either this quantitative relationship comes from the a priori error analysis, or at least you get some intuition in what you should do in order to get this kind of relationship. So that's all I'm going to talk about today, and I'm going to completely neglect any discussion of the CC residual. That's a whole talk on its own. Okay, so the outline for the rest of this talk, of course, I have to introduce what the CC equations are. So what is the mathematical formulation? Unfortunately, a lot of the analysis looks a bit messy, so you need to be familiar with what my notation is. Then I'm going to talk about the existing a priori analysis as it exists in the literature today. I need to do this because I want to justify why we are doing what it is that we're doing. Which is the next section. So I'm going to talk about the new results that we have. And then I'm going to give you some food for thought, so some follow-up questions, some open problems, etc., etc. Okay, so the mathematical setting. Well, we begin by taking two numbers. So we have n, a natural number. This is supposed to denote the number of electrons. We have k, which is going to be the number of single particle basis elements. So in principle, we could be in the complete basis set limit, in which case k will be infinity. And once we have that, we define a single particle basis set. So this is just a collection of L2 orthonormal orbitals. Each of these are elements of H1. We call this set B. And using this, we can define our n particle basis set. So for that, we need an index set just to make sure that we're not double counting and everything is labeled properly. But basically, the n particle basis set is defined by taking all possible determinants of these single particle functions. Okay, and you'll notice in all of this that I'm completely neglecting spin. This is by design because these slides become even messier if I start including spin. But in principle, the analysis here covers spin. It should be phrased in the terminology of generalized spin orbitals. Okay, so once we have these two basis sets, we can define the single particle space. So that's just V, it's the span of B. And we can define the n particle space. That's something I'm going to call Vk, and this is the span of Bk. Okay, so the object we're going to study, I mean, everyone here knows what it is. It's the electronic Hamiltonian H. Everyone should know what it is, I hope. I'm going to make two assumptions about this. One is the standard one, that the nuclear charge is greater than or equal to the number of electrons n. So this is completely standard. I'm going to make a further assumption, which is perhaps a bit restrictive, which is that the ground state of this Hamiltonian is simple. So we don't have any degeneracy. Unfortunately, we need this for the analysis. There's no way around this. So we have to live with that. What I would like to point out from a mathematical point of view is that you can treat the Hamiltonian as a mapping from H1 to H minus 1 that is bounded, number one, and number two, it satisfies the guarding inequality. So these are properties that we need for the analysis. I don't think I referenced them explicitly, but in the proofs, these are used in various places. So just as a reminder that this is true. Then, of course, we have the usual full CI problem statement. We're trying to solve a minimization problem. The only key thing to keep in mind here is my notation. So I'm going to denote the full CI ground state energy by E full CI star, and I'm going to denote the ground state wave function by psi full CI star. All right, so obviously this problem is computationally intractable. Everyone knows this, so we need some further approximations, and we introduce the notion of excited determinants and excitation indices and coupled cluster and CI in order to deal with this. So that's what I'm going to do next. So I'm going to start by defining excitation index sets. The way I do this is I pick a number between 1 and n, so I call this j, and then I have a set of indices. And these indices are basically rows of numbers. So we have two rows of j numbers each. The numbers at the bottom are supposed to represent occupied orbitals, so they'll be between 1 and n. The numbers at the top are supposed to represent virtual orbitals, so they'll be between n plus 1 and k. And once I have a set ij here, I can take the union of all of these and I get my full excitation index set. Okay, so once I have the excitation index set, I can define excitation operators. And the way I do this is the following. So I pick some excitation index mu. It has this form, so it's j numbers, two rows. And then I define it corresponding to this an excitation operator x mu. This is a mapping from Vk to Vk, so from the n particle space to the n particle space. And it's defined by its actions on the basis set. So how does it act on specific determinants? And it acts in the way that you would expect. So you have a given determinant psi nu, so basically you replace all of the occupied orbitals here with the virtual orbitals here. And this gives you a new determinant, and that will be the output of when x mu acts on some given determinant psi nu. And of course, if some occupied orbital is not present in your determinant psi nu, then the output is 0. If some virtual orbital is already present, then the output is again 0. Okay, so very natural. So a few remarks about this. So in all of this construction, I have taken for granted that the reference determinant is constructed from the first n orbitals. The second point is that our n-particle basis set, it has a very nice decomposition, so you can write it as the union of a reference plus all of the excited determinants, and the excited determinants come from the action of excitation operators acting on the reference, right? So you have this very nice decomposition, and this means also that your n-particle space has a decomposition which consists of the span of the reference determinant and the span of all of the excited determinants. And just FYI, as notation, I'm frequently going to write psi mu to denote the determinant which is constructed when you take the excitation operator x mu and you apply it onto the reference determinant. Okay, so now let's get down to some theorems. So this one is from 2013. It basically shows that excitation operators are in infinite dimensions, are bounded, you know, they have the right properties that we need in order to do any kind of analysis. So more formally, what we do is the following. We define a coefficient space of vectors. So these are sequences of real numbers which satisfy a certain property. The property we want is that if you construct a wave function using the sequence of real numbers, you take a linear combination which, based on these sequences, then the resulting wave function should be in H1. So these are not just square summable sequences, you have a bit more than this. And you take this coefficient space and you equip it with the norm that you would get by looking at the H1 norm of the corresponding wave function that you construct. So you have sequences of numbers and you have a norm associated with that, which I'm going to denote here. So once you have this space, then you can start to prove things, and this is what Roveda proved in 2013, that the excitation operator T, which is made up of, you know, taking these coefficients and then taking correspondingly excitation operators x mu, that this excitation operator is bounded as a mapping from Vk to Vk equipped with the H1 norm. And you can also prove that the D excitation operator, which is the L2 adjoint of this guy, is also bounded as a mapping from H1 to, well, as a mapping from Vk to Vk equipped with the H1 norm. Furthermore, you can show that you can extend this to the dual space. So at least the excitation operator T, you can extend it continuously as a mapping from the dual space Vk star to Vk star. And finally, if your coefficient vector T is only an element that's square summable, it's not in the special coefficient space, then both of these maps are mappings from L2 to L2. So everything is more or less bounded, and this is what we need. Following this, we have the standard result that is at the heart of coupled cluster theory. So it's the theorem that if you have a wave function which is intermediately normalized, so you take the inner product with respect to your reference and you get 1. If this is the case, then there is a unique excitation operator T. It's of this form, so it's a linear combination of, you know, these excitation operators x mu, such that if you take the exponential of T and you apply it to your reference determinant, you will recover exactly this wave function that you're looking for. And a particular corollary of this is that if your full CI wave function has this property, if it can be intermediately normalized, if it's not orthogonal to the reference, then there is an unknown coefficient vector T star such that if you take exponential of T star and you apply it to the reference, you will recover the full CI ground state wave function. So this is really what CC is about. You have to find the T star that corresponds to the full CI wave function. And how do you find that? Well, you have to solve a system of nonlinear equations. So these are the equations you have. The goal is to find this vector T star, which is an element of this coefficient space that I introduced, and it should satisfy the following properties. So basically, you have a similarity transformed Hamiltonian. So this is what this object is. It's acting on a reference determinant. You are testing it with all excited determinants, and you're setting the output equal to 0. So if you solve all of these equations, you will get, in principle, you should get, or you hope to get, T star. And once you've solved this equation, then you can just use an expression to derive the coupled cluster energy. Of course, in practice, no one solves this equation. This is completely untruncated. Usually you do a truncated version of this equation, but yeah, that's the main idea. Okay, so 15 minutes. Right, so now I'd like to dive into, so with all of this notation in place, I'm ready to finally dive into the existing a priori error analysis for coupled cluster. So in order to do that, I'm going to start by defining the coupled cluster function. So this is the object that we're going to study. So this I denote by F. It's a mapping from the coefficient space. So it takes as input some coefficient vector and it maps to the dual space of the coefficient space, V star. And it's defined as follows. So basically you take, again, your similarity transformed Hamiltonian, you apply it to your reference determinant, and then you test it against excited determinants, and this is what your function should look like. Okay, and what you're interested in now, if you compare to the previous equation, is zeros of this function. because the exact T star satisfies the property that this is equal to 0, so that's what you're interested in. So what is the current approach for analyzing this problem in the literature? So I cannot overemphasize the importance of Reinhold Schneider here, because he really laid the foundation for what people are doing in this field. So basically, Reinhold had the idea that you should try to show that this function f is locally strongly monotone at T star. So what does this mean? This means that you need to show that there exist two constants, gamma and delta, such that if you have any two coefficient vectors r and s, which are sufficiently close to the exact solution, T star, then you have the following property. You're basically that you take f of r minus f of s, you have a duality pairing, you're testing this with r minus s. This should be bounded below by the norm of the difference of r and s. So it's a kind of a positivity or bounded below result. So this is what you should try to show. This was Reinhold's idea. And if you are successful in showing this, then there are a lot of interesting consequences that follow. So you can prove, based on this, well-posedness of the full CC equations. You can prove, based on this, well-posedness of the truncated CC equations, which is what people really solve in practice, at least under some assumptions, if your excitation ranks are high enough and all that. Furthermore, you can devise, you can prove, error estimates, or at least a priori error estimates for the CC energy, for the CC amplitudes, all of the good stuff that you would want. You can do all of this. I mean, I have these as 2 bullet points here, but it's not trivial. It requires some work, but what I want to emphasize is that this property here is at the heart of everything that comes afterwards. And of course, if you want to develop potential a posteriori error analysis, then this constant gamma, this local monotonicity constant, is the thing that will link the residual to the error, to the CC error, right? So it's important to know what gamma is, how it's constructed, and all of that. So now I would like to show you what the argument actually looks like. My claim is that there's a few caveats here. Okay, so how did Reinhold prove this? So basically, it's Taylor series. The reason it's Taylor series is because there is not much else that you can do. You have this nonlinear, horrible function, the coupled cluster function. It has the full electronic Hamiltonian, which is not a nice object, and then it's being acted on by these exponential cluster operators. So there's not much you can do, right? So you do the only thing you're allowed to do, which is Taylor series expansion. So you take two input coefficient vectors, r and s, you expand your coupled cluster function around T star, so you get the following expansion. So the 0th order term goes away, it cancels out. Then you have the Jacobian of f acting on r minus s, and you have higher order terms, and I don't care about the higher order terms for the moment. Yeah, I assume that r and s are sufficiently close to T star so that they don't matter. So now if you input this into your duality pairing, into the thing you want to prove, you will get a first order term here involving the Jacobian, and you will get higher order terms. And now what you would like to show ideally is that this guy is bounded below by the norm of r minus s. So you can plug everything in and you can see what you get, and it turns out that this expression 1 here is of the following form. So it's basically a shifted Hamiltonian. So this time you have h minus the full CI energy. It's similarity transformed, and it's acting on the left and on the right on some excited wave function w psi 0. So w is some excitation operator, psi 0 is your reference, okay? So you would like to show, it's a bit like a kind of a Rayleigh quotient kind of thing, so you would like to show that this guy is basically bounded below. So what do you do next? Well, again, there's not much that you can do, so you do the thing that seems obvious, which is that you basically open up the exponential. And this gives you a 0th order term involving h minus e full ci, and then it gives you first order terms and higher order terms, and again, you just completely neglect the higher order terms, or you assume that they're small enough so that they don't matter. Now you plug everything in back into your duality pairing, and you will get a 0th order term, which is denoted in blue here, and you get a first order term, which is denoted in red. Now, my claim is that the blue term is good, so we're happy about that term, right? The reason for this is that this guy is actually coercive on the space of wave functions orthogonal to the full CI. Now, this test function here, or the trial function, is not exactly orthogonal to the full CI, but if your reference determinant psi 0 is close to the full CI, then you're exciting your reference, so you will be somewhat orthogonal to the full CI. So this term, you can argue up to some weighting, is basically positive, okay? And then the problem comes because this term you have no idea how to handle. You don't know what the sign is, you don't know if it's positive, you don't know whether it's negative, so you do, again, the only thing you can do, which is Cauchy-Schwarz. And if you do Cauchy-Schwarz, you will get two operator norms, and you will get the norm of the function that you want. So to sum everything up, basically you're able to get an estimate of the type that you want, except that the constant here involves the difference of two terms. You have a positive term in blue, you have a negative term in red. Next, what you do is you use continuity of these cluster operators, T and T dagger, and this allows you to pull out the norm of the amplitude vector T star outside. And now, so the way it works is, obviously, if this T star is small, then we can expect the red term to be small, and therefore the blue term will be bigger. We'll get a constant which is positive. And assuming that T star is small, or the norm of T star is small, is actually not an unreasonable assumption, because chemists already know that coupled cluster tends to work very well when your Hachi-Fock is relatively close to your full CI. So if it's a minor correction that you need, then CC tends to work well. And if you have a lot of static correlation in your problems, in which case the Hachi-Fock is a bad reference, then CC doesn't work well. So it's not unreasonable to assume that T star is relatively small. So that's what's done. You assume that the norm of T star is relatively small, so that the terms, basically the blue term balances out the red term, and you get a local monotonicity constant of the following form. Okay, so what's the catch? I mean, this sounds like everything is fine. So, I mean, the problem is, I guess you probably anticipated this. You can start to run actual simulations and try to compute these constants. So you do this for very small, very well-behaved molecules, right? Like water, boron hydride, stuff that we know CC works well on. And what you'll discover is that the term in blue, theoretically, is about 10 to the power, it's O of about 10 to the power minus 2. The term in red, well, you have three terms in red. You have the operator norm of H minus E star full CI. So this is about O of 1 because you're in the right norm. You have this guy here, the norm of the cluster amplitude vector. So this is also small. So as I said, this assumption is fine. You're already starting to see some problems, but the kicker is the fact that these continuity constants grow exponentially in the number of electrons. So as soon as n is bigger than 5 or 6, these guys here, they're orbiting Mars. I mean, there's no way that you can expect this constant to be positive, right? Now, you might think that this is because you're using a very coarse continuity estimate, and this is true. If you don't use continuity to get this T star, and you stick with the operator norm of T of T star minus T dagger of T star, you get better estimates. But you're still in trouble because things don't really balance out. You have a smaller positive contribution, and you have a much larger negative contribution. So this is not nice. Okay, so some remarks about this. First of all, this is the original argument that I showed you, but nearly all of the analysis that I've seen for coupled cluster, it uses versions of this argument. You have a similarity transformed Hamiltonian, you rip it apart somehow, and then you have a positive term that is good, and you have the term with no sign, and the only thing you can do with that is Cauchy-Schwarz. So this is pretty universal. And this means that almost all arguments for showing local strong monotonicity, they use the fact that T star is very small. And to me, it seems that this is a really restrictive argument, which means that you cannot really get practical constants with which to do a posteriori error analysis, right? And based on my experience with numerics, actually, if you do any kind of Cauchy-Schwarz estimate, it's already way too coarse. You're already gone, and you're not going to get a nice positive constant. Okay, so the bottom line is that we do not even have, in my opinion at least, a guaranteed positive local monotonicity constant for the coupled cluster function. So, I mean, we're miles away from getting a posteriori error estimates. Okay, so I'd like to propose, that we change tracks a little bit and do something slightly different. So I don't know if people have already guessed what it is that we should try to do, but I'll try to ease you into it. So I'm going to begin with a very straightforward lemma. So this is concerning the coupled cluster Jacobian. So basically, if you think of, you take any coefficient vector t, you look at the Jacobian of the coupled cluster function at this coefficient vector t. It's a mapping from v to v star. And then you can show that it satisfies the following property. So basically, the action of this guy on coefficient vectors can be characterized by the action of a commutator involving the Hamiltonian similarity transformed acting on some wave functions, okay? And this, you can call this entire thing A of t. And what you've discovered basically is that the Jacobian, it induces a linear operator between function spaces. So here in this setting, basically W and S, just to remind you, are coefficient vectors. Capital W and capital S are excitation operators that are made up using these coefficient vectors so that you get functions here, here, and here. And we've introduced a linear map. So it's A is a linear map, and it's a linear map from Vk tilde to Vk tilde, and just to remind you, Vk tilde is the span of excited determinants. Now, a particular corollary of all of this is that in the special case when t is equal to t star, so the full the correct CC cluster amplitudes, this A of t star, it has a very nice expression. It just boils down to taking a shifted Hamiltonian and doing a similarity transform of that. Okay, so you get this very nice expression. And this looks nice. I mean, if you're a numerical analyst, you will start rubbing your hands at this point because you know what to do next. So you look at everything that we have done up to now, and you look at what people are trying to do, and you look at the expression for the Jacobian that we just developed, and you realize that basically proving local strong monotonicity of the function f is nothing else than showing that this operator A is coercive in the sense of linear PDEs. And therefore, if you want to show that the function f, the coupled cluster function f, is locally invertible, which is the thing we want to show, then it's enough to show that this operator A of t star is an isomorphism. You don't need that it's positive, actually. And one of the lessons you learn very early on in boundary integral equations is that a lot of times it's easier to show an inf-sup constant exists than to show a coercivity constant exists. So that's exactly what we decided to do. We decided to show direct invertibility and develop some kind of inf-sup estimates. Okay, so one final comment I'd like to make about this is that this A of t star is actually a non-symmetric operator, so you have a choice. You can try to show that A dagger, the transpose, is bounded below, or satisfies inf-sup, or you can try to do the same proof with A itself, and it turns out that one is easier than the other. They're equivalent, but in some cases you can prove things, in some cases you cannot. Okay, so I have the following proposition. So what you can show is that A of t star as a mapping between Vk tilde and Vk tilde star. So a mapping from from the span of excited determinants, the dual space of the span of excited determinants is injective. So in other words, for every trial function, there exists a test function such that the duality pairing is not equal to 0. So this is a proposition that we can prove. I'm not going to show you proofs because it's mostly algebra, so all you see are a bunch of excitation operators floating around and daggers being exchanged here and there, so I don't know how interesting that is for people, but we can do it on the blackboard afterwards if you're interested. But the idea of the proof is actually simple. You just argue by contradiction. You use things that you know about the excitation operator. You use known orthogonality results. And eventually you are able to show that if A of t star acting on some phi is identically 0, then phi must be in the span of your reference determinant. But this is a contradiction because by definition phi is in the span of the excited determinants. So the fact that you get this is a contradiction, and this means that you've proven injectivity. It's not a super difficult thing to prove, but yeah, we can show this. Okay, second theorem you can prove is that if you take now the adjoint of A of t star, so this is A of t star dagger, then you can show that this guy is bounded below. In other words, there exists an explicitly characterizable constant upsilon greater than 0 such that, A of t star dagger is bounded below with respect to the right h1 and h-1 norms. Okay, so what is the idea of the proof? Well, it's the same as any inf-sup argument. Basically, you get a magic idea that you should try a particular test function. You input that test function. In this particular case, it turns out that the test function you should take is, you take your trial function phi, you apply exponential of minus t dagger to it, you apply exponential of t to this. This is the test function that you want. Unfortunately, you cannot take this test function because it's not in your test space. So you have to take a projection of it to bring it back to your test space. Then you add and subtract the things that you're kind of missing out. A lot of terms drop out, many things cancel. You have to use, again, known properties, simple properties, but known properties of the full CI wave function of the exponential operators. And finally, in the last step, you again use the coercivity of H minus E star full CI on the span of the orthogonal complement of the full CI wave function. So you can do all of these things, and you are able to prove that the adjoint operator A of T star is bounded below. So at this point, it just becomes a classic functional analysis, really. So you have an adjoint which is bounded below. That means that the adjoint is injective. It means that it has closed range. From the previous proposition, we know that the original function A is injective. This means that the adjoint also has dense range. So this is a consequence of the Hahn-Banach theorem. So you have an adjoint which has dense range, it's injective, it has closed range, that means it's invertible. And if the adjoint is invertible, then the original function is also invertible. So in effect, we have proven the following corollary, that the original function a of t star as a mapping from vk tilde to vk tilde star is invertible, and the inverse of this guy satisfies the following bound. It's less than or equal to 1 over epsilon. And this means we have proven the following theorem under the following assumptions. Assume that your ground state energy, E star full Ci, is simple. Assume that your ground state wave function is intermediately normalizable, meaning that it is not completely orthogonal to the reference that you pick. Then we know the following things. The coupled cluster the coupled cluster function is locally invertible at T star. This is what we wanted. And furthermore, the Jacobian of this guy is an isomorphism, and the inverse of the Jacobian satisfies the following estimate. That it is less than or equal to 1 over a constant epsilon. And we know what epsilon is. I have it written down here. So what are these constants? First of all, there is a weight here, which I'm calling omega. So this comes from the ellipticity constants satisfied by the electronic Hamiltonian. So this, theoretically, we know what this is. Yeah, there are estimates for this. Then this here, lambda 2 minus E star full Ci, is the spectral gap. So this is also not so surprising. Spectral gaps usually pop up in estimates of this kind. And then finally, we have a term in blue, and these are operator norms. These are operator norms involving exponentials. Okay. So yeah, we have constants, we have invertibility, we have what we wanted. And the nice thing about this theorem is that we don't need very restrictive assumptions. We just need simplicity of the ground state, and we need the fact that our reference is not completely orthogonal to the ground state wave function, to the full Ci ground state wave function. Okay, so what is the good and what is the bad? So what we've shown, as I said, is that the Jacobian is an isomorphism with a provably positive inf sup constant epsilon, and this means that we now have access, at least in theory, to a posteriori error estimates. So for any coefficient vector t which is sufficiently close to the exact coefficient vector t star, you have the following estimate. You know that th minus t star is less than or equal to, this is provable by the way, so this is guaranteed as long as th is close enough to t star. So it's less than or equal to 2 times. You take the Jacobian of f, you take the inverse, you bound this, and you multiply it with the norm of the residual. And we have a bound now for this, which is just 1 over epsilon. Okay, so we have this. So this is the good part. We have some idea what to do next to get a posteriori error estimates. The bad part is that we have, at this moment, no idea how to compute this constant epsilon in a tractable way. I mean, we can compute it, sure, but it's expensive. And the reason it's so difficult to compute this is, I mean, it's non-trivial, right? You have a spectral gap, which is, not a nice object to deal with, but okay, even if you were able to do something there, get some estimates of some kind. You also have operator norms, and these guys are difficult to compute, right? So there's at least three big problems here that I'd like to emphasize. So one is that these operator norms are with respect to H1. These are not L2 operator norms. So how do you compute H1 operator norms? It's not so easy. If you're in finite dimensions, you can use a single particle operator to kind of get an equivalent norm, which is what Reinhold did in one of his papers. But if you're in infinite dimensions, I mean, computing H1 norms is not so easy, right? So we're not sure what to do exactly there. The second thing is that these operators, they act on the full Ci space. So they have excitations of all ranks. I mean, they really talk to everyone, right? So this is also, it makes it a bit tricky. And the final thing is, I don't know if you noticed this or not, but the cluster amplitude vector T star is actually unknown. It's the solution, it's the thing that we want, okay? So this makes it a highly non-trivial problem how to approximate or get bounds on this constant epsilon that we now have. Okay, so next I'd like to change gears a little bit and move to finite dimensions. And why I'm doing this is because basically we decided that it might be a good idea to get some further insight or to get some qualitative estimates of some kind if we move to finite dimensions and maybe use different norms and see what we're able to say there. Okay, so now I'm going to assume that we're in finite dimensions. Everything I did before, I mean, the reason we had all of these norms and all that was so that we could say something about the infinite dimensional case. Now we assume that k is less than infinity. And in this particular case, if you use the L2 topology, it's possible to go a little bit further. Okay, so basically the fact you use is that T and T dagger, the excitation and the de-excitation operator, they're adjoints of each other. They're L2 adjoints of each other. They're not H1 adjoints of each other. And you're able to prove using this the following results. So actually here there's not much new, but okay. So you can prove that the adjoint of A, so A T star dagger, is bounded in the L2 topology. And this time you get constants which are a little bit nicer. I claim that they're a little bit nicer. So to start off with, there is no weight here, omega. You just have the spectral gap. And then this is multiplied with a ratio of different norms. These are norms involving exponentials acting on your trial function phi. Now, I claim that this is greater than 0. This is absolutely true. The reason is that everything here is an invertible operator, so you can kind of pull things out, but I don't want to do that yet. I want to simplify this expression a little bit more. At this stage, this looks a lot like the H1 norm, but it's going to get a bit easier. So basically what you can use is the fact that the numerator, the term on top, is basically an inner product. It's an inner product with respect to the L2 norm, and you can kind of pull one of the excitation operators to the other side, so you get a de-excitation operator. And then if you compare this guy and you put him here, you see that you have an expression that you want to bound from below, and this looks a lot like a reverse Cauchy-Schwarz inequality. Okay, so maybe we can say something about this, and it turns out that we can. So we denote by lambda min and lambda max the minimal and maximal eigenvalues of this guy here. So this is exponential of T dagger acting on exponential of T. We know that this is symmetric positive definite, it's bounded below, etc., etc. So these guys are positive and non-zero. And then we can prove the following thing. We can prove that the expression that I showed you on the previous page, the purple expression, it is bounded below by 4 times the minimum eigenvalue times the maximum eigenvalue. You take the square root, you divide by the sum of the two. So you get a very nice expression for what this guy is. And the proof, I mean, again, it's not rocket science really, but you do an expansion in terms of this operator, exponential of T dagger, exponential of T. You get an expression involving various coefficients. And then you go to the literature from the 50s and the 60s, and you find people who are interested in bounding sums and products of different kinds, and you discover that there is one inequality which applies really in this case, and you're able to pull out this very nice result. Okay, so this means we've shown basically that if you're in finite dimensions and you think of all of your objects as, vectors and matrices, then we have a bound on the inverse of the Jacobian, on the norm of the inverse of the Jacobian. And I thought it would be a good idea at this stage to kind of plug things into PySCF and see what sort of constants we can expect. So these are some very simple molecules. So you're constrained a lot by the size of your full CI, because in order to compute these things, especially in order to compute the inverse of the Jacobian, you really need the full CI solution and all of that. So there's a limit to how big your system can go. So these are just proof of concept examples. Okay, so what I do is I compare this constant to the exact constant here, right? And the ratio is given here. We know theoretically that this should be greater than 100%. But what is surprising perhaps is the fact that it's not so bad. It's actually a pretty decent upper bound, I think, for the theoretical constant that you get here. And there's a few features of interest in this table that I would like to point out. So one is that the quality of this bound doesn't seem to depend on the energy, on the full CI energy. So that's nice. We know, well, we suspect, at least based on these results, that it doesn't degrade as you increase the energy. It also doesn't seem to depend too much on what the spectral gap is. It turns out that the thing that determines how good or bad this ratio is actually the size of these two eigenvalues. So the bigger lambda max is and the smaller lambda min is, the worse this ratio seems to get. And lambda max and lambda min are basically representative of how big your coupled cluster correction is. So if lambda max and lambda min are the same, then it means that your exponential is basically the identity. If the largest eigenvalue and the smallest eigenvalue are the same, then you just have identity. So that means there's no coupled cluster correction at all. So the bigger this guy is from 1 and the smaller this guy is from 1, that means the bigger your coupled cluster correction is. And these results seem to indicate that the bigger your coupled cluster correction is, the worse this estimate gets. But it's actually, yeah, I mean, nitrogen, I think it's known it's not a very good choice for a coupled cluster, but we still seem to get pretty respectable, I think, results. Okay, so I am close to wrapping up. I have 40 minutes. Okay, I think I will do maybe 5 minutes and then make up for the fact that everyone had to come back from lunch early. So, okay. Right. So, the reason I showed this L2 stuff is because we were hoping that we get some insight into how to actually compute epsilon 2, you know, these constants that we have floating around. And unfortunately, we haven't really obtained this. I mean, it's easier to compute these guys than to compute the Jacobian of the couple cluster function. That's true, but the scaling is still not so good. And in effect, we have the same exact problems that we had before. We have an amplitude vector T star, which is not known. And even if it was, we have these matrices, which are k choose n times k choose n. So yeah, not exactly very pleasant. And the other problem, of course, is, I don't know if I mentioned this before, but there is, yeah, exactly. So there is a theoretical estimate for what this guy should be. So this comes from the theory, right? But the problem is that this theoretical constant, as I said before, it explodes exponentially. So we cannot really use this. So what I want to show in the last 2 or 3 minutes is basically that the situation is not completely hopeless. There are things that we think we can do. We just need to formalize them more concretely, and we need to figure out some gaps. But I think that there is a reason to be optimistic. So I am going to show you just one of these. So let's assume for a moment that we are given some approximation, some approximate amplitude vector th, which is finite dimensional, so it's in some subset of the excitation index set. And now we want to compute this guy. So this is a problem of computability. You know, I said we don't know what T star is, but suppose you know what T star is or you have a good approximation of it. How do you compute the maximum eigenvalue of a huge object? So we discovered that there is a very straightforward strategy that gives surprisingly decent results, which I'm going to share with you here. So what you do basically is you take the exponential of t of th acting on psi 0, and you call this wave function psi r. Okay, and then you can show that you can write this exponential, the norm of this exponential operator, as 1 plus, well, you add and subtract identity basically. Okay, so it's very straightforward, and this tells you that the norm of this guy is exactly equal to 1 plus the norm of this of an excitation operator r. And what is the property of this excitation operator r? The property is that when it acts on the reference determinant, you get exactly this wave function here minus the reference. Okay? So once you know that this is true, I really don't show any proofs, but I can do it on the board later. You can use tricks from discrete convolutions to argue that this operator norm here can be bounded by an L1 type estimate. So the reason you can do this is because the action of cluster operators on wave functions, it's a bit like a convolution. So it really looks a lot like what you do in Fourier. So the natural thing to do there is to use a clever Cauchy-Schwarz and then to kind of pull out an L1 estimate. So you can show that basically this operator norm is bounded by the L1 vector norm of the difference of this wave function psi r, which was defined here. It's coming from the action of the exponential on the reference, minus just the reference. And this is an L1 vector norm, and these guys are much, much easier to compute. You just have to sum over a bunch of entries. And the reason this is easier to compute is because we have assumed here that th, the thing we have access to, is finite dimensional, right? So you just have to sum over a bunch of finite dimensional terms. You have to combine them in various ways to account for the exponential, but this is much, much more practically doable than computing the maximum eigenvalue of a huge matrix. So this might seem like a coarse estimate, and I suppose it is a coarse estimate, but it turns out that if you actually plug it in, you seem to get surprisingly good results and at least an improvement over what exists theoretically, right? So these are 2 examples that I'm showing. I take the same molecules as I took before. I have 2 references, so I take here the exact T star, so this is the exact couple cluster, this is the exact couple cluster solution, T star. I look at the exact norm of this guy, the exact operator norm, and I use this L1 vector bound that I just showed you, which is quite easy to derive. And I compare that with the theoretical operator bound, just to show the gain we get. And I do the same thing with the finite dimensional coupled cluster amplitude vector. So this is something that you would typically have access to, just as a proof of concept to see what you get when you compute the exact operator norm versus what you get when you compute the L1 vector norm. And while I'm not claiming anything at this stage, so this is really something we're actively looking at, but at least it seems we get something much, much better than what the theory would suggest. And all of these bounds are guaranteed. So The only reason we might not be super optimistic is we might expect that L1 is not a good measure of the norm of this guy, but at least it's guaranteed. So it seems that if we try to use these bounds, we might be able to get somewhere. Okay, so time to summarize. Yeah, okay, I think I'm right on time. Right, so what have we achieved? Well, my claim is that under rather general assumptions, I don't know if this is the general opinion here or not, but I think that we don't have overly restrictive assumptions. We have shown that the CC function is locally invertible in a neighborhood of the exact solution T star, of course. We have also obtained a guaranteed positive bound for the inverse of the Jacobian, which is something we wanted for a posteriori error estimates. And in principle, at least, I mean, we could use this bound if we found a way to compute it. We could use this bound or approximate it. We probably can't compute it, but at least approximate it. We could develop a posteriori error estimates going down this route. So this looks kind of okay-ish, but what I'm cheating on is that we have like a huge bucket list of things that we really need to do in order to get to full error bars. So in particular, we still require a cheap computational method for evaluating the continuity constants that I showed you before. We do not have this. We have some ideas that seem to work well in some situations, but we don't have something systematic that we're completely happy with. Of course, the second thing that I didn't touch at all in this talk is we need a way to compute the coupled cluster residual, which is highly non-trivial. I mean, there are ways you can approximate this, but yeah, it's a whole talk on its own how to achieve this. And finally, I mean, everyone who does a posteriori error analysis probably knows this, but the residual actually has a special structure. So if you want to have sharp estimates of some kind, you need to take into account the fact that the residual has the structure, and you need to develop continuity constants for the Jacobian or the inverse of the Jacobian on these special subspaces. So this is, for example, something that I recently saw in a paper by Gaspard and Antoine and Eric. So yeah, these things matter if you want to get sharp bounds. Okay, so I think I'm on time, more or less. So thank you for your attention.